Two sheets of metal left out in the rain for 10 years. One of them is a rusted ruin, orange and flaking, slowly crumbling back into the dirt. The other looks almost new. They are made of nearly the same steel. The only difference is a coating on the second one, thinner than a sheet of paper, of a dull gray metal that made a quiet decision. It chose to rot instead of the steel, and it is still rotting in the steel's place right now. That same gray metal is sitting inside you as you watch this. It is folded into the proteins that read your own deoxyribonucleic acid, holding them in the exact shape they need to work. Without it, some of those proteins would fall apart, and the machinery that runs your cells would stop. And in the places where people get just a little too little of it in their food, it is a matter of life and death. By one widely cited estimate, a shortage of this single metal is linked to the deaths of around 500,000 young children every year, from a problem that a supplement costing a few cents can help fix. Here is the strangest part. People made coins and jewelry out of this metal for around 2,000 years without ever knowing it existed as a metal at all. They used it constantly and had no idea it was there. Its name is zinc. It is gray, cheap, and forgettable. The fourth most used metal in the world after iron, aluminum, and copper, and almost nobody ever gives it a second thought. Which is a shame, because its whole genius, the thing that ties this entire story together, is that it gives itself away. Before we start, sit with 4 questions. How does a coating thinner than paper save almost all the steel on Earth from rusting to nothing? By deliberately destroying itself first. How can the same gray metal pour electricity out of a battery and stand guard over the genes inside your cells? How does a small shortage of an ordinary element in an ordinary diet quietly kill hundreds of thousands of children? And why is it so cheap to stop? And how do you use a metal for 2,000 years without knowing it is there? By the end of this, a metal roof, a battery, and your own body are going to look different to you. Because zinc, the metal nobody thinks about, may be the most selfless element in the periodic table. Start with rust, because rust is one of the quiet enemies of everything we have ever built. Steel is the skeleton of the modern world. It holds up our bridges, our buildings, our ships, our cars, the pipes under the street, and the towers over the city. But steel is mostly iron, and iron has a deep, patient wish. It wants to go back to being ore. Left to the air and the rain, iron combines with oxygen and water and slowly turns to rust, crumbling, weakening, flaking away. Given enough time, rust eats everything we make of it. The whole steel civilization is, in a sense, always trying to dissolve. And this is not a small problem. Economists who study corrosion have estimated that the cost of rust and its prevention runs into the trillions of dollars a year, on the order of a few % of the entire world's economic output. Every year, a slice of everything we build has to be repaired or replaced, simply because iron will not stop trying to become ore again. Rust is one of the largest, slowest, most relentless taxes the physical world charges us. And the main thing standing between us and a far bigger bill is zinc. So how do you stop it? You could paint the steel, but the moment the paint chips, the rust creeps in under it and spreads. What you really want is something cleverer. And the answer, found more than a century ago, is to wrap the steel in zinc. We call it galvanizing, and by most measures, it is where the largest share of all the zinc we mine ends up. Dip the steel in molten zinc or coat it, and you get that familiar, dull, silver-gray finish you have seen 1,000 times without noticing. On guardrails, on buckets, on nails, on the corrugated roofs that cover a large part of the world. That humble, ridged sheet, corrugated galvanized iron, is one of the quiet building blocks of the modern world. Light, cheap, strong, and rust-proof, it spread out from the factories of the 19th century to roof warehouses, farms, shanties, and whole towns across the tropics and beyond. If you picture the roofline of a fast-growing city almost anywhere in the world, a good part of what you are seeing is steel kept alive by zinc. It is not a glamorous material. It is simply one of the most useful ones ever made, and it works because of the gray coating almost no one thinks about. At first, it just looks like a protective skin, a barrier between the steel and the weather, and it is that. But zinc does something far more remarkable, and this is the heart of the whole story. Zinc is chemically more eager to corrode than iron is. It is, in the language of chemistry, more reactive. So when the two metals sit together and the weather comes for them, the oxygen and the water go after the zinc first. The zinc corrodes, and the iron underneath is left alone. Now here is the beautiful part. Scratch that zinc coating, gouge it, drill it, cut the steel so the bare iron is showing. On a painted surface, that scratch is where the rust would begin. But on galvanized steel, the exposed iron still does not rust, because the surrounding zinc keeps sacrificing itself to protect it. The zinc gives up its own atoms into the corrosion, feeding itself to the reaction, so that the steel does not have to. Engineers call it sacrificial protection, and the word is exactly right. The zinc is not a shield the steel hides behind. It is a substitute that dies in the steel's place. There is even a second layer of cleverness to it. As the zinc surface corrodes, it does not just crumble away like rust. It forms a tough, stable gray film of its own corrosion products, a patina that clings to the surface and slows down any further attack, protecting the zinc that remains underneath. The coating manages its own slow sacrifice, stretching it out over years and decades. The idea was patented back in the 1800s, and the name we gave it, galvanizing, ties it forever to the early pioneers of electricity, whose story is coming in a moment. You can see this idea taken to its purest form out at sea. The steel hull of a ship, sitting in salt water, is under constant chemical attack. So shipbuilders bolt lumps of zinc onto the hull below the waterline, and to the rudders and propeller shafts. These are called sacrificial anodes, and their entire job is to corrode. The salt water eats the zinc blocks instead of the ship, and every so often, when the zinc has been eaten away, divers simply bolt on fresh ones. The same trick guards underground pipelines, and it is probably in your home right now, as a zinc rod hanging inside your water heater, quietly being consumed year after year so the steel tank does not rust through. Step back and look at what that means. A huge share of the metal skeleton of our civilization, the steel that would otherwise be crumbling into rust, is being kept alive by a thin layer of a cheaper, humbler metal that has agreed to be destroyed in its place. We almost never see it. We never thank it. It just quietly rots so that something more important does not. And that turns out to be the one thing zinc does better than almost anything else. It gives itself up, which is exactly what it does, in a completely different way, the moment you put it inside a battery. In the year 1800, an Italian physicist named Alessandro Volta stacked up a strange little tower, discs of zinc and discs of copper, one after another, separated by cloth soaked in salt water. And out of that quiet stack of metal came something the world had never had before, a steady, continuous flow of electric current. There is a famous quarrel behind that stack. A few years earlier, another Italian, Luigi Galvani, had noticed that a dead frog's leg twitched when touched with two different metals, and concluded he had found a kind of animal electricity, a life force in the tissue itself. Volta disagreed. He suspected the electricity came not from the frog, but from the two metals and the moisture between them. And to prove it, he built his pile out of metal and brine, with no animal anywhere in sight, and it produced current all the same. Both men ended up immortalized in the words we still use. We measure electric push in volts after Volta. And when we coat steel in zinc or jolt something to life, We say we galvanize it, after Galvani. Before Volta, electricity was a party trick. A spark, a jolt, a crackle from a rubbed piece of glass, there and gone. Volta's stack, which we now call the Voltaic pile, gave a current that kept flowing, on and on, that you could actually work with. It was the first true battery, and it opened the door to the entire science of electricity. Within a few years, other scientists were using piles like it to pull apart water and discover brand new elements. In England, Humphrey Davy built enormous batteries on this principle and used their current to tear apart compounds that had never been broken before, pulling out elements like sodium and potassium for the first time. A tower of zinc and copper had handed chemistry a new key to the universe, and the beating heart of that first battery was zinc. Here is what is actually happening inside. In a battery like Volta's, the zinc is the part that gives. Its atoms dissolve, releasing their electrons to flow out through the wire as electric current, while the copper simply receives. The zinc is not powering your device by holding on to itself. It is powering it by taking itself apart, atom by atom, and pushing the pieces out as electricity. It is the same selfless act as the coating on the roof, only now the sacrifice comes out as a current you can use. That basic bargain never went away. The ordinary batteries that ran flashlights and radios for a century, the zinc-carbon dry cells, work on the same principle, with a case of zinc slowly being eaten from the inside to power the thing in your hand. The tiny button batteries in many hearing aids are zinc-air cells, pairing zinc with oxygen straight from the atmosphere, prized because they pack so much energy into so little space. Wherever you needed cheap, reliable power in a small package, zinc was quietly there, spending itself. And now, 2 centuries after Volta, zinc is being asked to give again, on a far bigger stage. As the world tries to store electricity from wind and solar, engineers are taking a hard new look at zinc-based batteries for the power grid. The appeal is exactly what it always was. Zinc is cheap, it is abundant, and unlike some of the fashionable battery metals, it does not want to catch fire. The oldest donor of electrons we ever found may end up helping to hold up the electric grid of the future. But long before Volta ever stacked his disks, people had been using zinc for thousands of years for something completely different. And the truly strange thing is that all that time, they had no idea they were using a separate metal at all. Go back to the ancient world, and you will find brass where? Bright, golden, handsome brass, in coins, in ornaments, in armor and fittings. Brass is an alloy, a mixture of copper and zinc, and it has been made for well over 2,000 years, which raises an obvious question. If the ancients were making brass, they must have been using zinc. So why did nobody know zinc existed? The answer is a lovely piece of chemical sleight of hand. The old way of making brass did not use zinc metal at all. Instead, craftsmen heated copper together with a zinc-bearing ore, a mineral called calamine, packed in with charcoal. At the right temperature, the ore gave up its zinc, but not as a shining liquid you could pour and admire. The zinc came out as a vapor, an invisible gas that soaked straight into the hot copper and turned it golden from the inside. The zinc did its work without ever once showing its face. People made brass by the ton and never held the metal responsible for it. That golden alloy was valuable enough to matter to empires. The Romans prized a bright brass they called orichalcum and struck some of their coinage from it. And for centuries, a well-made piece of brass could pass to an untrained eye as something close to gold. Zinc was, in a quiet way, the secret ingredient of counterfeit gold long before anyone could name it. When Europeans finally did start to give it a name, in the 16th century, the physician Paracelsus called it something like zinken, and the label stuck. But naming a metal and truly understanding it are two different things. For a long time, zinc was a word for a stubborn mystery, and that vanishing act is exactly why zinc was so fiendishly hard to isolate on its own. To pull a metal out of its ore, you usually heat the ore with charcoal, and the metal melts in pools at the bottom. But zinc breaks that rule. Zinc boils at a temperature lower than the heat you need to free it from its ore. So at the very moment you finally tear it loose, it is already a gas, rushing up out of the furnace. And the instant it meets the air, it burns and turns straight back into a useless powder. For centuries, anyone trying to smelt zinc in the ordinary way watched it simply disappear up the chimney. To catch it, you have to do something counterintuitive. You have to lead the hot zinc vapor away from the fire and let it cool back into liquid metal in a sealed space, with no air to burn it. That is a genuinely difficult trick, and here is the part of the story that gets left out of a lot of Western textbooks. The people who first cracked it on an industrial scale were not in Europe. In the region of Zawar, in Rajasthan in India, metalworkers built furnaces that did exactly this, condensing zinc vapor into metal using rows of sealed clay retorts in a downward distillation process. By many accounts, this was happening on a large, organized scale from around the 1200s onward, centuries before Europe managed the same feat. The hills around Zawar are still heaped with the slag of that ancient industry. India was smelting pure zinc as a deliberate product while European chemists were still arguing about whether it was even a distinct metal. Europe only caught up much later. It was in the 1700s that a British entrepreneur, William Champion, patented a commercial zinc smelting process in Bristol, and a German chemist, Andreas Marggraf, is often credited with clearly demonstrating how to isolate the metal and studying it as an element in its own right. Only then did the Western world formally recognize that this gray stuff, which had been hiding inside their brass for 2,000 years, was an element of its own. So here is zinc, halfway through its story. A metal so shy it made brass for millennia without being seen. So slippery it escaped every furnace as vapor, finally pinned down and named. But while European chemists were busy proving it existed, zinc was already doing the most important job it has ever done, in a place none of them thought to look, inside living bodies, including theirs. There is a lot of zinc in you. After iron, it is the most plentiful trace metal in the human body, somewhere around 2 to 3 grams of it spread through your tissues, and it is far from idle. It is working constantly, in ways we only really came to understand in the last several decades. Its most elegant job has a beautiful name: zinc fingers. Many of the proteins that read and control your deoxyribonucleic acid need to fold into a very precise shape to grip the genetic code, and a huge number of them use a single zinc atom as the pin that holds that fold in place. The protein wraps around the zinc like a hand closing around a small stone, and that grip is what lets it reach into the double helix and switch genes on and off. Take the zinc away, and the hand cannot close. Right now, as you sit here, countless tiny zinc atoms are holding your genetic machinery in working shape. This was only worked out in the last several decades. The structure was first described in the 1980s by the biologist Aaron Klug and his colleagues, and it turned out not to be some rare oddity. Zinc fingers are one of the most common shapes in the whole toolkit of life. A large number of the proteins that switch your genes on and off rely on them, which means that a surprising fraction of what makes you, in any given cell at any given moment, is being held together by little pins of zinc. For a metal we mostly think of as roofing material, that is a remarkable second job. That is only the start. Zinc is a working part in more than 300 different enzymes, the molecular tools that drive your body's chemistry. Your immune system leans on it heavily. So does the healing of wounds, which is why zinc is turned up in ointments and creams for generations. It is tied to growth, to fertility, and to something you might not expect: your sense of taste and smell. People who run short of zinc can find that food goes flat and dull because the machinery that detects flavor needs the metal to work. This is part of why, when you feel a cold coming on, you may find yourself reaching for a zinc lozenge. The evidence on whether zinc actually shortens a cold is genuinely mixed, and researchers still argue about it. But the reason people keep trying it is real. Zinc matters to the immune system, and a body short of it defends itself less well. And you have met zinc on your own skin. That thick white paste a lifeguard wears on the nose is zinc oxide, and it works as a physical sunscreen, sitting on the skin and turning away ultraviolet light rather than absorbing it chemically. The same compound soothes rashes in calamine lotion and in the cream used on babies, although in a very zinc-like twist. The single biggest industrial use of zinc oxide is not on skin at all. It is in rubber, where it helps the tires of the world hold together. And zinc is scattered all through your ordinary day in metal form too, usually where you least expect it. It is cast into the zippers on your clothes, the keys in your pocket, door handles, toys, and countless small die-cast parts. Because molten zinc alloy flows into fine molds beautifully and cheaply. In the United States, even the humble 1-cent coin is, since the early 1980s, almost entirely zinc, wearing only a thin skin of copper. The penny in the bottom of a drawer is really a little disc of zinc in disguise. Once you know to look for this metal, you start finding it everywhere, quietly doing its job and taking no credit. So the metal that rusts to save your steel and dissolves to power your battery is also quietly standing guard over your genes, your immune system, and your sense of taste. It gives itself to you too. And that is exactly why the places where it goes missing turn into a slow catastrophe that most of the world never sees. If you have ever fought off a cold with a zinc tablet or read the back of a sunscreen bottle, tell me in the comments whether you knew this humble metal was doing all of this at once. I read them. Because for a very large number of people on this planet, there is not quite enough of it. And what happens then is one of the quietest tragedies in global health. Zinc does not stay in the body for long. We have no big storage tank of it the way we bank some other nutrients. That means you need a steady supply every day from food. And the best sources are things like meat and shellfish, which a great many people in the world cannot eat very much of. Diets built heavily on grains can be low in zinc and can even contain substances that make what little is there harder to absorb. The result is that, by many estimates, on the order of 2 billion people worldwide are at risk of not getting enough zinc. Often they have no idea. It is not dramatic. It does not announce itself. It shows up as children who grow more slowly than they should, as immune systems that cannot quite hold the line, as bodies that struggle to heal and to fight off infection. Nutrition experts have a name for this kind of shortfall, where people get enough calories but not enough of a crucial nutrient. They call it hidden hunger. You can be fed and still be starving for a single gray metal. It falls hardest where you would expect, in regions where diets depend heavily on grains and where meat and shellfish are luxuries, and where the soils themselves are often low in zinc, so that the crops grown in them carry less of it to begin with. Much of South Asia, much of sub-Saharan Africa, pockets of poverty on every continent. The people most affected are rarely the ones writing the headlines, which is part of why this stays so invisible. A shortage you cannot see, in the food of people the world tends not to look at. And for the youngest and most vulnerable, that weakness can be fatal. When a child who is already short on zinc catches an ordinary infection, the illness hits harder and lasts longer, and is more likely to kill. The link is strongest with diarrhea, still one of the leading killers of young children in the poorest parts of the world. A gut lined with cells that need zinc to repair themselves, in a body whose immune defenses need zinc to function, simply cannot cope as well. When researchers tried to put a number on it, the number was staggering. By one widely cited estimate, for the year 2004, zinc deficiency was linked to the deaths of roughly 450,000 children under the age of 5 across Africa, Asia, and Latin America. By that estimate, it played a part in something like 1 in 7 of all childhood deaths from diarrhea. A shortage of a cheap, gray, unglamorous metal in the food of the poor, sitting among the largest killers of children on Earth. And here is the part that should stay with you, because it is not only a tragedy. It is a tragedy with an almost insultingly cheap solution. Giving a child a short course of zinc during a bout of diarrhea has been shown to make the illness shorter and less severe, and health agencies now recommend zinc alongside simple rehydration salts as a standard treatment. Zinc tablets can cost just a few cents. Efforts are underway on the other side of the problem too, breeding new varieties of wheat and rice that carry more zinc in every grain, and adding zinc to the fertilizers spread on depleted soils, so that the metal reaches people in the food they already grow and eat. It is a slow, unglamorous fight, waged with tablets and seeds and soil. But this is one of the rare killers in global health that you can genuinely push back with a coin. Look at the whole shape of it now. The same metal that gives itself up to save our steel, that takes itself apart to give us electricity, is the metal quietly holding children alive. And its absence, its simple absence from a plate of food, is enough to kill. In galvanizing, in a battery, in a human cell, zinc keeps doing the one thing it seems built to do. It spends itself so that something else can keep going. So what do you make of a metal like this? We rank the elements in our heads the way we rank everything. Gold is glamorous. Uranium is frightening. Titanium sounds strong and expensive. And zinc sits near the bottom of that list. A cheap gray nobody. The stuff of buckets and gutters and the back of a battery. It never gets a starring role. It has no romance to it at all. And yet look at what it actually does. It rusts on purpose so that the steel bones of our world do not. It dissolves itself into electric current so our machines can run. It hid inside brass for 2,000 years, asking for no credit. It folds into the proteins that read your genes and holds them steady. And where it is missing from the diets of the poorest, its absence alone is enough to take a child's life, while its presence, in a tablet worth a few cents, is enough to save one. Here is the picture I want to leave you with. A drop of rain runs down a plain metal roof somewhere, and under it, atom by atom, a layer of zinc is quietly corroding away so the house beneath it stays whole. At that very same moment, in a cell in your body, a single zinc atom is holding a protein in the exact shape it needs to read one of your genes. And somewhere in the world, a child swallows a small white tablet and, because of it, lives to see the next year. One metal, one quiet habit, spending itself in 3 different worlds at once. We spend a lot of time admiring the elements that shine, that explode, that make us rich. Maybe the one worth admiring most is the gray one that just keeps giving itself away and never once asks to be noticed. The most selfless metal in the world is holding your civilization and your body together right now, and you have almost certainly never thanked it. Thanks for staying with me. If this changed the way you see a plain gray metal you never thought about, hit like and tell me in one word what stayed with you most. Say roof for the coating that rusts so steel won't. Say spark for the metal that gave us the battery. Say brass for the element people used for 2,000 years without knowing it was there. Say cell for the atom holding your genes in shape. Or say children for the 500,000 lives a few cents could save. Pick one word and drop it below. Subscribe because the next element has just as many secrets hidden inside it. See you then.